Hello everyone. Today Deepak and I are going to talk about CanDID, our new decentralized identity system. This is joint work with authors from Cornell University, UIUC, and JP Morgan, and all the authors are part of IC3, the Initiative for Cryptocurrencies and Contracts. Let's begin with a brief introduction to the motivation behind CanDID and decentralized identity more broadly. First of all, existing identity systems are not necessarily user-friendly. Consider the case of making an account for a Bitcoin wallet. You need to do KYC, that's Know Your Customer, using video authentication and an ID card. But you actually can't hold it up like that, or like that. This is fine, because you're not covering part of the ID card or part of your face. But it turns out this is also fine. That is, a user could find an off-the-shelf deepfake software which are only getting better every day. How about the case of even simpler systems like authenticating yourself to an app using OAuth, such as using Facebook or Google accounts? This offers limited functionality, such as maybe only login. Also, this data can be controlled by third parties now and used for tracking, as shown by Engelhardt et al. In 2018. Note that these systems require some sort of issuing authority, such as a stable government, which leads to the exclusion of vulnerable populations such as refugees. Finally, storing identity data on enterprise servers is a liability, as evidenced by countless breaches and hacks, and the fact that it's our bread and butter as the security community. Notably, the Indian government's identity database, including over 275 million people's data, was hacked and exposed on the internet for over 2 weeks. To summarize, the goals for decentralized identity are improving user experience, reducing fraud, empowering users to manage their own data in a flexible way, to provide credentials to disenfranchised or stateless individuals, and reducing stored personally identifiable information and, as a result, enterprise liability. The basic setup for decentralized identity goes like this. There's a user, Alice, an issuer, such as the California DMV. Alice generates a public-private key pair, and the issuer issues an ID and binds it to Alice's public key so she can now use it. Now, say Alice wants to avail a service, such as getting a student loan. She can make claims about herself, such as, I'm Alice, I'm over 18 years old, I'm a California resident, and she can use her decentralized identity and secret key to confirm these claims. Now the bank checks this ID and decides to give her a loan. There is existing work on decentralized identity. In fact, it's a fairly active area these days. For example, the Decentralized Identity Foundation, whose members are wide-ranging from banks to digital passports. Also, W3C is working on a standard, and there's Hyperledger Indy, Evername, Uport, many other startups. The vision is that users will control their own credentials, digital passports, digital diplomas, proofs of age verification, etc., etc. So, why do we need another system to do decentralized identity? Well, several problems get swept under the rug in these systems. First of all, we talk about credential issuers. But where do these issuers come from? Without a bunch of issuers, it's not possible to build a robust decentralized identity ecosystem. But without a decentralized ecosystem being in place, there's no incentive for issuers to issue IDs. This is the classic chicken and egg problem. Also, users are notoriously bad at managing large keys. An estimated 4 million Bitcoin were lost due to this, and this is from 2017. Problem is probably much worse now. So you take a nice process of going from centralized financial systems to decentralized ones like Bitcoin, and then because users are trusting a service like Coinbase, which is centralized with their keys, you've basically centralized this financial system all over again. In fact, something like 10% of all Bitcoin is held in Coinbase. Finally, we want lots of issuers, but what we don't want is lots of copies of an individual. For example, applications like voting, which require one person, one vote. Sybil resistance is easier without privacy, as with everything. Even so, it's a hard problem, as evidenced by the research activity on the Sybil resistance problem. But you could leverage identifying information such as social security numbers. Once you do this, though, could you get privacy? And once you can do private Sybil resistance, could you get accountability, such as against financial crimes? To summarize, CanDID is a decentralized identity system which allows bootstrapping identity using legacy data, key management, and Sybil resistance with accountability. Now Deepak will discuss how we do this.
Hi everyone, this is Deepak and I'll take you through the rest of the talk. Before I go into CanDID, I'll first introduce a building block called Deco. I'll explain Deco through the following problem. Suppose Bob here is about to launch a new token called the bubble token, and he's going to hold a token sale. Bob has ideas about how to make the sale responsible. He wants to ensure that his tokens are fairly distributed, aren't all snapped up by a single person, and that people who participate can reasonably afford to do so. So he sets the following rule. To buy up to 100 bubble token, you have to show that you have a bank account with your name on it and it should contain at least $5,000. This makes it hard for people to create fictitious identities. Alice comes along. She would like to participate in this token sale. She has the required amount, but how does she prove this to Bob? A first thought could be to simply send a screenshot of her bank account. But as you all might know, it's easy to modify a screenshot. Alice might have no money, but still pose as a multimillionaire. So this won't work. Another idea could be to send the TLS transcript. Quite likely, Alice is interacting with the bank or a TLS connection. At a high level, this means the follows. TLS works in two phases. First, Alice and bank generate shared keys in the key exchange phase. Next, these keys are used to send messages across in the record layer. We are going to refer to these messages as the TLS transcript. For example, the bank balance Alice sees is also part of this transcript. So our idea here is that Alice can simply forward this TLS transcript to Bob. And perhaps Bob can just look at the transcript and check that the balance is greater than $5,000. Now, at first sight, this might seem like a workable solution. Recall that TLS guarantees transcript integrity, which means that the transcript can't be forged by a third party. That's sort of how Alice is sure that the data she receives from the bank isn't forged and it's actually coming from the bank. So perhaps a similar guarantee transfers to Bob as well. The problem with this idea is that the integrity guarantee is designed to be useful only for Alice, not to a third party like Bob. To explain the problem, TLS uses public key crypto or digital signatures for the key exchange phase, but switches to using symmetric keys for the record layer. And record layer integrity is provided through a MAC rather than a true digital signature. Essentially, Alice and Bank have a shared MAC key. But what this means for us is that Alice can use this MAC key to forge a transcript before forwarding to Bob. For example, to look like a multimillionaire. Now, there are a few proposals to change TLS. For example, the TLS-N scheme and the OpenID standard both allow signing of data. But changing TLS is not a viable solution in general because it requires big infrastructural changes, which means that we're basically back at the bootstrapping problem. The key idea in Deco is to withhold the MAC key from Alice. Essentially, Alice and Bob generate shared key K through what we call a three-party handshake. This ensures that Alice can't force the transcript she receives from the server. But later, once the session ends, Alice proves things about the transcript to Bob in zero knowledge. The cool thing about all this is that the server doesn't know this is happening, and as far as the server is concerned, it's interacting with just another web client. What Deco aims to do is liberate web data so that it can be used in blockchain systems and elsewhere. Specifically, we want a user to be able to log into a website via TLS and then prove statements about this data to a verifier using zero knowledge proofs. In our banking example, this statement could be that Alice has at least $5,000 in her bank account. I want to again highlight that Deco works without modifying existing TLS servers, and Deco also supports both TLS versions 1.2 and 1.3. With that, I'll move on to CanDID now. The basic setup in CanDID is that of a committee of nodes, and we assume a fraction of them to be honest. Credential issuance in CanDID works as follows. Let's say Alice wants to get a credential that says that she's above 18 years of age. Now, Alice first gets to pick several providers of her choice. The only restriction on the providers is that they have a web interface where they show Alice's age that Alice can access. Alice uses Deco to prove to committee members that she is over 18. Once enough committee members verify the Deco proofs, they issue a signed credential saying that Alice is over 18. In this process, we've essentially turned any web server that serves web content via TLS into a credential issuer. Other nice credential issuance properties CanDID has include privacy, which is that the committee members learn only the attested data and nothing more. Legacy compatibility and virtually unlimited attestation types are supported. I'll move on to key management now. Recall that the goal of CanDID's key management system is to provide a usable yet decentralized alternative to existing ones. Roughly, we take a similar approach in key management as that of credential issuance. Alice can back up her secret key with the committee, who store it via standard secret sharing techniques that ensure that no individual node learns the key. If ever Alice loses her key, she goes to several pre-selected providers of her choice, provides a proof of login generated via Deco, and once enough committee members verify these proofs, the key is returned back to Alice. You might be wondering why not use OAuth, and the reason we do not use more standard protocols like OAuth is that they leak information that we think would be undesirable in a decentralized identity system. For example, the committee nodes might learn users' real-world identity, which could be potentially undesirable. Moving on to Sybil resistance now. Recall from the token shell example before that we somehow want to ensure that each user gets only 100 bubble tokens so as to ensure a fair distribution of tokens. CanDID takes two approaches to providing Sybil resistance. The first is what I'll call the unique ID approach, where user begins with an already unique identifier, for example, the social security number. The committee has a PRF key, and a PRF is computed over the social security number, the output of which is matched with an existing deduplication list. If no match is found, the user is unique. Finally, the new entry is added to the list. Note that the PRF key is secret shared amongst the committee members, so no individual committee node knows it. The use of PRF essentially ensures that even committee members don't learn the social security number. Essentially, what we get out of this approach is that one ID gets one candidate credential. A second approach to Sybil resistance is what we call the fuzzy approach. And the motivation here is that several people lack a unique identifier. This could, for example, be belonging to countries that don't provide them. And identification for these people relies on things like name and address. The problem with these identifiers, though, is that they're prone to all kinds of errors, for example, transcription errors. Therefore, these identifiers require techniques like edit distance or more broadly fuzzy matching. An example transcription error is shown in the picture on the right. As noted before, doing fuzzy matching is easy if privacy was not a concern. The challenge in CanDID is to do fuzzy matching while keeping user data hidden from the committee nodes. In a nutshell, CanDID instantiates a fuzzy matching technique called C-shingles using secure MPC. The details of it can be found in the paper. At a high level, what happens is that the committee holds a database, for example, of let's say usernames, and when a new user, say Scrooge McDuck, comes in, the committee uses fuzzy matching techniques to find if the user belongs to this list. Note in particular that the database is held in secret shared form, that is, no individual committee node knows it in full. Finally, it turns out that the same fuzzy matching techniques are also useful for accountability, let's say to prove that you're not in a public sanctions list. Again, we won't cover it in detail in the interest of time. We implement CanDID and perform end-to-end measurements. The credential generation time is less than 20 seconds, well within the realm of practicality. This time includes using Deco to port credentials from two websites, SSA and Rent Cafe, and also the time to perform deduplication. Another number I want to discuss is the sanctions list check time. This check involves using the fuzzy matching techniques we've developed. As you can see, it is somewhat expensive, taking about 25 minutes. But this is one time, and there are opportunities to heavily parallelize it in order to reduce it further. Thank you for listening. Please visit our website to learn more.